Let's start today's lecture with an example on scalable computing. So here I have a Jupyter Notebook on Dask. Dask is a library in Python that allows us to do scalable computing very effortlessly. So first, I'd like to acknowledge Matthew, Jacob, and Tom, whose codes are used in this Jupyter Notebook. So Matthew Rocklin is the CEO of Coil and the developer of this great Python library. First, let's start with out-of-memory data processing. So here I have my personal computer. It has maybe 16 gigabytes of RAM. And let's say I want to process some data that is larger than my RAM. Can I do it? Yes or no? Who says yes? Who says no? All right, so pretty much everyone's skeptic, at least. So let's see if we can actually do that. So first, I'm just importing some visualization package. So I guess all of you are familiar with the NumPy library. So here I'm importing NumPy and creating an array with a size of 100 times 1,000 times 1,000. So it's going to create it for me in a matter of a second without any errors or anything. But if I ask NumPy to create an array for me with this size, so 100,000 times 1,000 times 1,000, I'm going to get an error. So who knows what this error is telling us? You can raise your hand if you want to answer. I can answer it myself. So the array that we wanted to create was larger than the memory. And the error says, well, I want to create it, but I need 745 gigabytes of RAM to create it. So this is very typical. So now what we can do instead of NumPy is using Dask array. So Dask array is a data structure in the Dask library, and its usage is pretty much similar to NumPy. So pretty much what we know about NumPy and how to use it applies to Dask as well. So here I'm creating a Dask array with that size. And you can see that it doesn't give us an error at the least, right? So pretty much what it's providing is not the array itself, but kind of a blueprint ensuring us that I know how to do it. If you really want me to generate this at the right time, I will generate it. But I will generate it in sort of a scalable way. So this is the array. It says that the total memory it's needed for this is 745 gigabytes. But Dask is going to generate it in those tiny chunks, as you can see. And those chunks are going to fit my memory. Not only they fit my memory, but actually Dask is going to kind of create a computing cluster on my laptop with a number of workers, maybe 4 workers or 8 workers, depending on how many threads I have in my CPU. And actually, these chunks are going to fit the memory of each of those workers. So now we can actually generate such a large array of random numbers and do any process that we want with it. So let me give you another example. So here, I'm creating a NumPy array. This time I'm just using a 2-dimensional array of 20,000 by 20,000 so that it fits the memory. And you can see that just generating it takes 5 seconds. Now if I want to do some basic matrix operation on it, for example, adding it to its transpose and then taking the sum of all the entries, it's going to take quite a while with NumPy. You know, it is still possible because it fits the RAM of my laptop, but you can see that it's taking quite a while. So, all right, let's see. So 14 seconds for processing it. So 5.3 seconds for generating it, 14.4 for processing it. So in total, something around 20 seconds, right, with NumPy. Now doing the same thing with Dask. So if I want to generate it, again, it's going to kind of give me a blueprint that I know how to do it. But actually, at this stage, Dask has not created it because Dask works on some sort of delayed processing. So only at the right time, it's going to generate those data and then process them and then keep the output and get rid of them to release the memory for the next chunk. So you can see that this part was pretty fast, pretty much instantaneous. And here is the process, the same operation. Again, it's going to give me some blueprint, not the result. It just says, all right, if I want to do this operation, it's going to involve 114 tasks. That's the number of kind of smaller tasks that the whole operation is broken down into. And those 114 tasks will be allocated to workers on my computer, maybe 4 workers or so, and they will do this processing in parallel. All right, so now let's time it. So when we want to actually get the result from Dask, we need to type .compute, telling them that I don't want the blueprint, I want the actual result. Now when we run compute, Dask is going to do 2 things. First, it's going to generate the data from the blueprint, and then it's going to do the processing. So here, when I run this, you can see that with Dask, the whole thing takes 4 seconds compared to 20 seconds. So 4 seconds is both for generation of the data and the processing, including the transpose operation, which is quite intensive. So you might be wondering what's happening under the hood. So this is pretty much what's happening under the hood. So with Dask or with, let's say, parallel computing, what we have is like some kind of central node and then a number of workers. So here we have 6 workers. So this central kind of computing unit is going to use that blueprint and then break the task into small pieces and then allocate those tasks to different workers. And every now and then, the workers need to do some communication, as you can see. So they do some communications to maybe aggregate some partial results. And in the end, there's going to be quite a lot of communications to just bring everything together for the final result. And this is also the usage of computing resources for those six workers, as you can see. So this is a typical situation, not exactly what happened to our task, to our process, because we had 114 smaller tasks. So if you exactly want to know what was going on, this is what was going on. So for that operation, for that matrix operation and 114 tasks, this is what happened. So we had that data frame or data set with 25 chunks. Each of those chunks, some work is needed for them. That's how we ended up with 114 tasks. Some of them are just aggregation tasks. Some others are things like maybe summing the entries of a matrix or finding the transpose for some part of a matrix and so on. So now let's move on to part 2 to better understand a flowchart like this. But before that, do you have any questions? No? All right. So with distributed computing, what we try to do is essentially delay the computations so that different parts of a larger process can be processed in parallel by different workers on the same machine, or probably on a cluster. So that's the other thing. So what I'm doing here is essentially high performance computing using my laptop, which is definitely possible. So if you have a laptop maybe with some CPU from the past couple of 5 years, probably it already has 8 threads, 8 virtual cores. This means that it is capable of doing 8 operations at the same time. So in many situations, when you want to process some large amount of data, you can use Dask on your laptop so that you get a speed up of 8 times. So I mean, it kind of depends, the speed up. Sometimes it's less than 8 times, or sometimes it could be even more, depending on the process. But I guess the first kind of learning outcome of this session is knowing that high performance computing can be done on a laptop. All right, so Dask has something called Dask delayed. So Dask delayed is a method that we can apply on functions so that the function calls for those, let's say, lengthy, like time-consuming functions happens in parallel. So let's start with a simple code. So this is without any Dask. So this chunk of code, as you can see, I have 3 functions. Inc, which just increments the input by 1. It takes x, it adds 1 to it, but also it sleeps for 1 second, meaning that it just makes the CPU wait for 1 second. Then the next function is double. As you can see, again, this one sleeps for 1 second and then doubles the inputs. Then the third function, add, takes x and y, so 2 arguments, and then sleeps for 1 second and return their sum. So as you can see, each of these functions are going to take 1 second plus something, right? Because they all involve 1 second of sleeping. So now if we want to run this on a data set like this, 1, 2, and 3, where we have a for loop, first we take the inc of this, so increment 1, then double the result, then double 1, and then add the result of those 2, right? So for input 1, we have 3 function calls. Then for input 2, 3 function calls. Then for input 3, again, 3 function calls. And in the end, we're going to take the sum of all the 3 outputs from these 3 inputs. So how long do you think this loop is going to take in total? More than 9 seconds, a bit more than 9 seconds, because we have 3 inputs. For each of them, we have more than 3 seconds when these are done in sequence, right? So Python just runs your code in sequence normally, unless your code is written in parallel, only if the code is in parallel, it's going to do parallel processing. Otherwise, for this, it's going to be in sequence. That's why it takes a bit more than 9 seconds. So I'm running it, and I'm timing this chunk of code. And as you can see, it's going to take a bit more than 9 seconds, right? It's 9.05. 9 seconds is just the time that the CPU was asleep, and that 0.05 second was the actual time of adding things and incrementing things and taking sum and so on. All right, so now with Dask, we can just use this idea of delaying a function. And here I have the same functions, but I'm kind of wrapping them in delayed. So these are the same functions. They are defined in the previous chunk. So instead of computing A as inc of x, I'm computing A as the delayed result of inc of x. So now if we run this, you can see that it gives us some cryptic output. Anyone wants to guess what this is? You should already know. I pretty much covered it in the previous part. Whenever we ask Dask to do something, it is going to first give us some, let's see if, all right, maybe this doesn't help. So it just gives us maybe some hash output for the place in the memory that this is going to actually put the result. So when we ask Dask to compute this, to actually just ask it for total, initially it's going to just give us the blueprint. It kind of says, trust me, I know how to do it. Whenever it's time, I will do the actual computations. For now, just take this address in the memory. That's where I'm going to actually put the result whenever you really want me to do the operation, right? So far, Dask has not done anything. So now, if we want to visualize the process, we get a flowchart like this, which is hopefully a bit easier than the previous one. So we had 3 functions. We had a double function, an inc function, and then the result of those, these are like intermediate results. We need to add them for another result, and this kind of branch here is just for input 1, this is for input 2, and this is for input 3. And then the results of these will be then again aggregated in a sum, and that would be the final result. So this is kind of the process that Dask is going to actually use. So on my computer, I guess it's going to use 4 workers at a time. This means that maybe in the first second, Dask is going to just give this thing to worker 1, worker 2, worker 3, worker 4. Maybe the next second, worker 1, worker 2, worker 3, worker 4. So far, there's only 2 seconds, and I guess this part and this part here will be done after 2 seconds. Pretty much something like this. I'm not entirely sure because, based on how these are connected, Dask is going to actually find the best way of allocating these circles to workers, so that the result, let's say these 3 adds, are done when this sum is supposed to be calculated. Or even, if it is needed, and these 2 adds are done, maybe first it aggregates them and then adds the result of this one to it. Actually, the whole purpose of Dask is that we don't need to worry about these things because it takes care of all of them for us. So maybe with kind of traditional libraries for parallel programming, you needed to actually care and design these things. Now Dask takes care of all of them for us. So now if we want to really get the result, we need to type .compute, and you can see that the whole thing takes 2 seconds, as we were kind of expecting based on that flowchart. So instead of 9 seconds, we got 2 seconds, which is quite substantial. Maybe if this was 9 hours and 2 hours, right? Maybe that's kind of more tangible for us to see the benefit. Any questions? Yeah.
Well, you set the number of workers to 1.
Yeah.
You get 9 like the previous.
Yeah, I guess we get 9. Yeah. Yeah. Because with 1 worker, we can only do sequence. We can only do the computation in sequence. Yeah. Yeah. My impression is that we had 4 workers here. Okay. So, any other questions? All right. Let's move on to part 3. So how many of you are familiar with k-means? Raise your hand if you know what k-means is. All right. So for those of you who don't know k-means yet, k-means is a clustering algorithm. The idea is, pretty much something like this. Let's say we have some data points that are kind of clustered automatically, like they are in kind of a modular format. Like there's nothing going on here, nothing here, nothing here. So they are kind of separated. And this is in 2 dimensions. Like we have some x2 and x1. And in 2 dimensions, actually, we're not going to really use k-means. If we just check the scatter plot, we can see that this is 1 cluster, this is the 2nd cluster, this is the 3rd cluster. But if we have data with more dimensions, meaning more features, let's say 10 features, we cannot really visualize it like this, and we cannot see the clusters this easily. That's why we need something like k-means or a clustering algorithm. So what k-means does is, first, it's going to just consider 3 random centroids. So 1 random centroid is here, let's say another random centroid is here, and a 3rd random centroid is here. And maybe these are like, we can call them A, B, and C. And then it's going to allocate each of these data points to the centroid that is closest to them. So maybe for this x in here, it will be allocated to cluster A because A is closer to this compared to this distance and compared to this distance, right? And then after these allocations, it's going to calculate the averages of the positions of x's belonging to a class, and that's how it finds new centroids. So maybe after 1 iteration, maybe these ones, I guess this one will be allocated to B, this one also to B, maybe this one will be allocated to C, right? But then A, B, and C, these centroids, we need to update them based on the positions of the x's belonging to a group. So maybe after this, B will move here. I guess A maybe moves here. And C, because some of these will be kind of assigned to C, C will be kind of taken down to here. And then we do another assignment. And we continue this iteratively. At some point, ideally, C ends up being here, B ends up in the center of here, and A ends up here. That's the ideal situation. But also sometimes this algorithm fails and doesn't give us the output that we expect. But if everything works well, we get a separation, let's say like this. So throughout the algorithm, these kind of decision boundaries move because the centroids change. So here is a kind of dynamic visualization of k-means. It starts with some initial centroids, and then over different iterations, the centroids will be updated, and then the assignments will be updated, and at some point, the algorithm kind of stabilizes, and it converges to this solution. This final solution that we have maybe after 12 iterations, this is 14 iterations. That was the final result. That was the final allocation of nodes into groups. So what is the purpose of this? So if we have, let's say, maybe something like maybe age and income, let's say for marketing, with clustering, we're going to see that essentially our customers, they belong to one of 3 clusters. We have, let's say, older people with like medium income. We have, let's say, we have another customer base who are rich and, maybe in terms of their age, they are somewhere in between. And we have this cluster who are young and poor people. right? And then for advertising, this allows us to say, all right, for if we want to just use some promotions or some marketing strategies that are designed for more price-sensitive customers, we better target them to our younger customers, right? And then maybe if we have some, I don't know, maybe some other marketing strategies which are for pricier products or whatever, we need to target them to this age group and so on. So that's one kind of example of what clustering is good for in an actual setting. So the thing is, k-means clustering, the complexity of it depends on number of clusters, number of data points, and all of these factors. So that's why when we run k-means on a larger data set, it's going to take much longer. So here I'm running k-means. Here I'm first generating some synthetic data on age and income. So exactly the example I provided. For n people in k clusters, this is just synthetic data so that they have some kind of clustered format to them originally, so that later the algorithm rediscovers those clusters. So this is just simulation. So the data looks like this. Actually, I'm creating them here, right? Just creating them takes so much time. I'm creating 1 million data points, right? So as you can see, the generation of this data takes 12 seconds, and I have these 3 clusters, right? So yeah, that's maybe age, and let's say this is income. So we have these 3 clusters. Now an algorithm that kind of detects that this kind of circle here is one cluster, that's another one, and that's a third one would be a successful implementation of clustering. Because we're not going to tell the algorithm where the data came from. It actually came from, a uniform, right, distribution of income, and yeah. So we had 3 clusters, right? For each of the clusters, we took a random value from the range of 20,000 to 200,000, and that became the mean of income. And then we took one random number from 20 years to 70 years, and that became the mean of age. And then we just generated data from a normal distribution with that mean and some standard deviation. This is the standard deviation. So maybe when the age was chosen to be 32, for one of the clusters, we created normal data with mean of 32 and standard deviation of 2. All right, so now this is the data, and if you want to run k-means on it, we can just use scikit-learn, that's a library in Python, and we just need to provide the valid number of clusters. And here, when we fit the model, you can see that it takes quite some time. So just generating the data took 12 seconds, and now this part seems to take quite a while. And this is just 1 million data points. In many situations, we work with larger data sets. So you can see that the clustering is done properly. I mean, except for maybe the midpoint of that, as k-means has limitations, the regions it's going to create will be all convex regions. So it cannot really find any sort of curve in there. But it's done something, and the wall time, the total runtime is 26 seconds. So 26 seconds plus 12 seconds, so 38 seconds in total with k-means from scikit-learn. So k-means actually in scikit-learn uses parallel programming for some parts of the process. Actually, the initialization of those centroids, that's very important for the result of k-means. If we start with bad centroids, then we may converge into some suboptimal, undesirable solution. I mean, in terms of optimality, we always end up with some suboptimal solution because this is just a heuristic. But maybe if the centroids are both here at the beginning, maybe we get stuck and they don't move. So that's why the initialization part requires a large number of trials. And for that part, the k-means function in scikit-learn actually does some parallel programming. But then for the rest, if I'm not mistaken, the rest is done in sequence, meaning that it's not taking advantage of all the computing power that your laptop has. All right, so now I'm going to do the same thing using a local computing cluster. So I'm going to create a local cluster. By cluster, I mean a computing cluster, not k-means cluster. So I'm going to create some computing network where I have one central node and 4 workers. Each of those workers will be one of the cores on my CPU. And then the work will be broken down between them and assigned to them, and then there will be communications and everything. So here, I'm just creating the cluster. So now the cluster is ready. This is like the address in the network for this local cluster. This is the address, the TCP address. There are 4 workers with 8 cores. This means that each worker can do 2 things at the same time. So this is worker 1. This is the address of worker 1. It has 2 threads. So worker 1 itself can do 2 things at the same time. So now if I want to do the same thing, so 1 million data points, here I'm actually creating them by typing .persist. So that doesn't only give me the blueprint, but actually generates the data. So it was pretty quick. Maybe it was 1 second or so. Now if I want to run k-means, it's the code is the notation is like this, pretty much similar to scikit-learn. So that's one advantage of Dask. That's pretty much what we know about pandas, NumPy, and scikit-learn are also useful in Dask because Dask uses the same names, same namespace and everything. So you can see that this one takes only 5 seconds. So now, if I want to just visualize them, I'm just visualizing some of the data points, just 1,000 data points, just to see the clusters. So this is how Dask works. And now that we're done with using those workers, we need to close the client. Now my laptop is back to normal process. Before that, each of those cores were kind of a separate identity. So whenever we open a cluster, we open a local client, we need to close it. All right, so this is pretty much the summary of what we talked about. So unfortunately, I didn't have anything to teach you so far today because you already knew them all. I guess you knew about NumPy. That's the first 2 lines in that chunk. And the same thing works with Dask. So if you want to create random number with NumPy, this is what you used to use. Now you can just use da.random. And it does the same thing. But under the hood, it takes care of all the parallelization and all the scalable computing things. You knew about pandas. You know how to open a CSV file with pandas. With Dask data frame, it's the same thing. You just need to type, instead of PD, you just type DD. That's it. And scikit-learn, I guess most of you were familiar with it. For example, for k-means, it works like this. You type k, you load scikit-learn as maybe sk, and then fit a k-means model on the data using k-mean.fit. With scikit-learn, you just load this as dsk, and then call k-means from dsk and fit. So yeah, that's why we didn't really learn anything new today, because everything with Dask is so convenient that all your knowledge of NumPy, pandas, and scikit-learn pretty much translates automatically to Dask. You just need to know it exists. Any questions? All right, let's take a 5-minute break and then we continue.